The introduction, Parker, and thanks to everyone joining in. Good afternoon, good evening. You're now attending a session called GT Suite Thermal Fluid and Multiphysics Simulation Software here at TFAWS in 2020, so thanks for joining. When we were putting together this presentation, thinking of our target audience, the target audience for this presentation is tailored to engineers that either use simulation software, might depend on simulation results, or heck, even if you're interested and want to learn something new, this is the right spot for you. So we're really excited today to be sharing this simulation approach for different applications, and one of those being kind of the topic of this TFAWS conference is thermal fluid simulations, and we'll also throw in some structural interaction. Looking at rocket engines and propulsion systems, cryogenic two-phase fluid systems, priming and water hammer, as well as some electrical components such as batteries, fuel cell, and the thermal interactions between those components. So I look forward to sharing all these topics with you here today. A brief kind of what we'll be talking about today. We'll start with who we are for those that may not know Gamma Technologies or GT Suite. Also, what we mean by thermal fluid multiphysics simulation. And then we'll be sharing a lot of different case studies, and hopefully these are interesting to you and show practical applications of simulation towards everyday problems. And some of those come from NASA, United Launch Lines, Airbus, and others. Towards the end of the conversation, we'll be talking and sharing a live software demonstration to give you a feel for what GT Suite looks like. And then we really love questions, so as Parker mentioned, please type in questions at any time during the presentation, and we'll address those towards the end. Also, another important thing, for those that are involved in simulation or have an interest, anyone that's attending today is eligible for a free GT Suite trial license. So this means the full feature GT Suite version for 30 or 60 days. If you are interested, we welcome you to reach out. You can type your contact info into the chat box at any time during the presentation, or you can contact me directly, John Zanker, at the email address shown there at the bottom, j.zanker@gtisoft.com. With that, I'll get right into it, and at least one thing that motivates me with all of this thermal fluid analysis is the global mission of what we're doing, and we're setting new history records here with human space flight. And these things are certainly very interesting, very historical, and it's great to see that thermal fluids plays a big component in these, in getting humans back to not only space, but perhaps farther planets like Mars. The two guys that will be presenting for you today within the next hour from the Gamma Technologies is John Harrison, my colleague, and John Zanker, myself. Now, we're certainly no rocket scientists or astronauts, but we have engineering backgrounds and a lot of experience with thermal fluid analysis in a lot of these applications. My colleague, John Harrison, who will be sharing the demonstration later, is the author of many technical papers, including those at past TFAWS presentations, AIAA, SAE, and many other journals. And me, John Zanker, am responsible for some aerospace industry business development here at Gamma Technologies, and have the joy of seeing a lot of these applications come to life. So what do we mean by GT Suite multiphysics? Multiphysics is a pretty common word that's thrown around simulation industry, and I'd like to give you kind of an understanding for what we mean when we talk about that. So within GT Suite, we have validated library components of different, that represent different physical domains. So the ones that may be more topical today are the thermal fluids on your left-hand side. And on the thermal side, GT Suite can represent thermal components with a 1D kind of lump mass approach all the way to a 3D kind of network. Even furthermore to a 3D finite element analysis. Representing fluids, we're proud of our world-leading 1D flow library that allows modeling of any species, including a gas, liquid, two-phase mixture, cryogenic or non-cryogenic. But there's also a lot of other systems that come into play, right? Electrical systems are usually a component of the larger systems, and GT Suite has libraries to construct simple electric circuits all the way to detailed components, including motors, power electronics, or for batteries. And usually in these systems, there's some type of chemical reaction, and that might be combustion, for example, in a rocket, or in a battery, the electrochemistry that occurs within a lithium-ion battery cell. And GT Suite has a built-in transient chemical rate-based kinetic solver that helps us solve all those problems. And we also show mechanical there on the bottom. Usually in a lot of components, there's something mechanical that's spinning, moving, or opening. And in the case of maybe fluid systems, we have a valve that may be part of that system, and there's some forces acting on the valve from the upstream and downstream fluids, and we can study that valve fluid structure and the dynamics between them. And the beauty of being able to model all these physical domains is rolling it into one model that allows us to integrate those domains so that we're accounting for not just one part of the problem, but all of the multiphysics that are occurring so that we accurately represent the system we're modeling. Perhaps we can implement some kind of controls logic to see if I command a signal, what will happen, not just on the component level, but the complete system, and what the transient behavior of that will be. I hope that paints a little bit of a picture, and this helps round it out as well. So in the area of multiphysics and CAE modeling, there's many tools and approaches to do different analysis. And if we look at this in a fidelity spectrum, the left-hand side is kind of represents the back of the envelope, Excel type kind of calculations for maybe some sizing, basic requirements. Over on the right-hand side, this is the other end of the extreme, which is a deep dive into 3D analysis. And this is usually only after we have some 3D CAD data available or 3D renderings. The challenge with the right-hand side is it can take a long time to run and make it hard to iterate and optimize complete systems. And so GT Suite fills this niche area in between 0D all the way to 3D and allows us to calculate complete system performance on the order of seconds or up to minutes for each scenario. And this includes transient 1D fluid dynamics, as well as transient 1D all the way to 3D thermal and finite element analysis. For those that have experience using simulation software, what makes GT Suite different is usually a question that comes up, and I'd like to hit on just a couple points, and then we can explain those in the cases that are coming up soon. The first one is easy to build models. The first step in any simulation is building models and accurately building those models. So GT Suite includes the ability to build models from scratch using a drag and drop approach to place components on a map and a sketch pad, if you will, and has predefined validated templates to represent, for example, pipes or fluid networks or compressors or pumps or mechanical components. An alternative way to build a model is if we do have CAD data available, we can directly convert that 3D CAD data available from whatever native CAD platform we have into a system of fluid thermal networks. Another thing that makes GT Suite different is the rigorous 1D Navier-Stokes transient fluid dynamics solution. So usually when we're studying large systems, we take a 1D fluid dynamic approach. And GT Suite is proud of it, being the industry leader in this area to solve all the governing equations that are involved in fluid problems, including conservation of mass, momentum and directional changes, energy, species, as well as humidity. There's also different fidelity options. So as we're building a model, we may have less data or more data for different components. And let's take a look at perhaps the thermal structure. We can represent that simply to start as a lump to mass. Or we can extend that out as we have more of a definition of our geometry as a finite element within GT, or even for those that currently are using finite element codes, you can also integrate that particular finite element simulation software directly within GT to look at boundary conditions or perhaps complete system performance. Also, the results within GT Suite are proven and validated. So Gamma Technologies has been around for over 25 years and has been thoroughly published and validated in many different public domain sources, including AIAA or here at TFAWS and other journals. And of course, there's usually talk of integration with other codes. So there may be some codes you might have that you'd like to integrate into a system level model, and GT Suite takes an open approach to that and allows users to enter their own or code their own code in any of the languages shown here, including Fortran, C, Simulink, even Excel, macros, Python, etc. So hopefully that gives a little understanding for some of the differentiators of a multiphysics simulation tool within the space. And next, a very quick introduction of Gamma Technologies, the company behind GT Suite. John Harrison and I are both talking to you from the headquarters of Gamma Technologies outside of Chicago. GT was founded over 26 years ago in 1994, and the only thing that Gamma Technologies does is software R&D of the tool we're talking about today, which is called GT Suite. We have offices around the world, including 3 offices in the US and multiple offices around the globe that help support engineers and scientists that are using GT Suite. And some of those organizations that are using GT Suite are shown up here on the screen right now, and one of those, of course, being NASA, as well as a good cross-section of space, aircraft, automotive, industrial, marine, and even agricultural businesses are using GT Suite to solve a lot of the similar problems we're talking about here today on spacecraft and space systems with fluid and thermal challenges. Just to give an understanding for those interested maybe in what NASA has been up to using GT Suite at NASA, and I singled out 3 centers. The first one being Langley, doing research into scramjet technologies and creating a nice model that represent a complete scramjet thermal management system to, of course, protect the combustor for the high heat loads that it sees. They also were using GT Suite for a lot of different thermal fluid problems, including complete energy management that included components such as batteries and motors. NASA Glenn uses GT Suite for a lot of different applications, a couple of them being fuel cell or electrolyzer systems that produce or generate electrical energy, fuel propellant line analysis, propellant or fuel tank thermal stratification, or even IVF system modeling, a novel concept I'll mention later. Also, NASA Marshall has been using GT Suite for a lot of different challenges, including cryogenic fluid thermal transients, as well as interaction of high velocity liquids and gases and its interaction with latch valves opening and closing, and how that sets up or creates different dynamic responses. And to round out the breadth of some other applications that are used in GT Suite, there's a lot of different applications in the realm of space propulsion, including fuel and oxidizer fuel kind of feed systems to rocket thrusters, including the turbo pumps that are included in those systems, the combustion that might occur at the rocket thruster using a more simplistic approach using equilibrium combustion, or alternatively, a rate-based chemical kinetics equation to solve for combustion. Other applications including helium pressurization systems and the transient dynamics, water hammer, surge analysis, tank thermal analysis to look at boil-off from the liquid to the vapor phase, line chill downs, many different applications on ground support systems, and also battery and thermal applications. Kind of zooming in on one of those applications, we're looking at a rocket engine and the propulsion system. So what we see on the left-hand side is a schematic, of course, of a rocket engine with the fuel tanks of liquid oxygen and liquid hydrogen. And there's turbo pumps in the system, there's heat exchangers, valves, and so on. And you see the representative system model in GT Suite on the right-hand side that consists of all those components: pumps, compressors, valves, feed lines, thrusters, and so on, all solving all the equations for fluid dynamics, heat transfer, combustion in that model in a transient way. And you may see some logic in there that is sensing and controlling the different components within that model. Another area GT is used is for electric and hybrid systems. So this kind of spans both space applications as well as terrestrial aircraft applications, but there's a lot of different concepts that are being explored using GT, and we can explore concepts from pure electric vehicle to eVTOL, hybrid systems, fuel cells, and within this domain of electrical, there's a lot of emphasis being done on detailed battery modeling, and my colleague John Harrison presented on that in a presentation this morning at TFAWS on high fidelity kind of thermal runaway analysis of the battery. There's also many different other applications that we see GT Suite being used for, including not just representing batteries perhaps as a map or performance set or maybe a RC equivalent circuit approach, but taking it to the next level to study what's going on inside the battery at a chemistry level, either in a 1D or 3D approach. And this allows us to predict really interesting results such as battery capacity fade or state of charge, looking at a predictive state of health results that come out of a battery after various charge, discharge, rest cycles. And you can kind of see a plot that I'll get to probably later in the presentation of looking at long kind of cycle runs of batteries with different thermal boundary conditions and how that might affect battery life. Also, E-component thermal management is a large component which allows us to study not just the battery thermal, but all the different systems that need some kind of active or passive thermal management, including power electronics or perhaps the electric drive motors. And now I'd like to get through some of the more interesting case studies. So thanks for bearing with me on the background. Jumping into the first case study that was used using GT Suite is a paper from Penn State that was published at the 2019 AIAA Propulsion and Energy Conference. This was a water hammer case study. So a common test within the propellant or rocket kind of validation phase is looking at kind of in the center of this image, a propellant tank boundary condition on one side that is high pressure propellant, a latch valve, and then kind of an evacuated empty manifold on the other side that might feed a downstream thruster. And so at a given time, that latch valve pops open very quickly, and we see this large pressure surge or pressure wave dynamic be set up that then travels to the thruster. And it's important to study this dynamic event because there's that high kind of pressure wave is important to know what the peak pressure is to protect our downstream components, but also perhaps to optimize and prevent maybe a large pressure spike using kind of more of a system design approach. So on the top image here that I'm sharing, and I'll turn on my my laser pointer, you're seeing kind of the nice correlation between GT Suite and some NASA test data looking at peak pressure spikes that may have occurred in that system at given different conditions, as well as the transient event on the scale of more of a millisecond kind of scale of that pressure spike as it occurs and goes to its peak pressure, and then that pressure decays throughout the system, kind of that classical water hammer case. And this paper shared a nice correlation between both measurements and the GT Suite test results for a given setup. Furthermore, another great case study was presented at AIAA in 2018 and relates to a cavitating venturi, which may be studied by itself or may be studied, of course, in a larger system to control fluid dynamics within a larger system. And we see in this paper that the predictive solution of this converging and diverging conical pipes with the venturi in the middle correlated very well to both measurements and CFD. And we took a 1D approach to discretize or mesh or divide that venturi along the length of that pipe section so that we're adequately capturing perhaps some of the vapor volume fraction within that as the fluid is cavitating. And you'll see on the bottom right-hand side, some of the results are comparisons to 3D CFD analysis, both in graphical and then more of in a pictorial way to share the nice correlation between a 1D analysis in GT and in this case, anti-fluent 3D CFD. But also comparing the results to NASA test data. And you can see here on the upper right-hand side, looking at the pressure drop across the venturi on the y-axis and the volumetric flow rate on the x-axis, and the great correlation at different delta P's within the test that showed the cavitation event and the great correlation between the data points that came from measurement and the lines that came from the GT suite simulation run. So these venturis, of course, can be modeled by themselves or included in a larger system simulation so we can study complete system transient behaviors and when those venturis may be cavitated. Another interesting study was done here at TFAWS 2 years ago. It was a propellant tank thermostratification and was done by NASA as well as some colleagues here at GT, including my colleague that will be presenting later, John Harrison. This looked at a fuel tank, and you can see a graphical representation of that fuel tank on the right-hand side. It's almost spherical in shape, and if we were to take kind of an axial slice, many different axial slices through that tank, we can discretize or divide that tank into many sections for the interest of looking at heat transfer from the walls to the fluid, as well as any of the ullage above the liquid fuel to look at effects of heat transfer within the tank and the effect of boil off that might be occurring from that liquid phase to the vapor ullage. So another very interesting kind of thermal fluid problem that showed promising results. This is another interesting one, and this brings together a lot of the multiphysics in GT suite. This is an integrated vehicle fluid system case study. It was presented by Roush using a United Launch Alliance integrated vehicle fluid system. So for those that aren't familiar with this IVF system, it's a system that includes hydrogen and oxygen feeding an internal combustion engine as a potential supplement for helium pressurization. So you'll see the schematic of the system on the bottom right kind of in a graphical way, and the left-hand side, the blue and green liquid hydrogen and LOX tanks, but also the lines that transport those fuels and oxidizers through heat exchangers, pumps, an internal combustion engine, a starter generator, and even a battery to store electrical energy. These are all systems and components of this larger system that needed to be studied, not standalone, but all integrated together to see if this technology would work in this demonstrator. And so all of these components, including heat exchangers, valves, lines, pumps, were represented within a GT suite model. And therefore, the engineer that was analyzing the system could not only look at right-sizing the right-size components for heat exchangers, but also look at complete system dynamics that might be occurring within a system like this. Again, I certainly welcome any questions you might have with any of these, and we can get to those at the end of the presentation. Please don't hesitate to type anything into the chat box. and we can get to those here soon. Moving right along, another case study. This one was changing gears to less of a fluid thermal system, but more to an electrical PEM or proton exchange membrane fuel cell example. This one was presented by NASA engineer Ryan Gilligan at both a past TFAWS event as well as a GT Suite conference. And in that case, Ryan developed a system model of a fuel cell to study the electrochemical performance of that fuel cell as hydrogen and oxygen were supplying the fuel cell stack, which then would convert the hydrogen and oxygen, of course, into electrical energy with the byproducts of water and heat generation. And of course, with any heat generation, we're concerned about some type of thermal management system. So there was a cooling system to cool the PEM stack. And you can see some of the nice validation results on the right-hand side. Looking at, on the top one, the electrical performance or the stack voltage that was coming out of this, this PEM fuel cell in a transient run with different loads. So you can see the test data in blue, as well as the red lines of the GT Suite simulation results correlate very nicely. As well as throughout that same transient event, looking at the thermal heat rejection and how the heat exchanger system is performing to keep that stack at optimal temperatures throughout the different electrical load kind of requirements of that given test. So another great test case of an electrical thermal fluid type of problem. Moving along to less of a space application, but a very cool application in itself. This was an electric vertical takeoff and landing kind of craft from Airbus A3. You may hear urban air mobility or air taxi used in discussion. A lot of these kind of large-scale quadcopters used for human flight transport. And you see the Vahana vehicle on the bottom right-hand side of this slide. It happens to have 8 electric motors, and those motors are motivated by only 2 battery packs. So it's a pure electric vehicle. And with that, there's high risk of different events of the electrical performance, of course, of the battery pack, but also the thermal performance and preventing thermal runaway that were studied in this complete vehicle model. So after we're able to build these battery packs using single individual cells to represent each cell of the battery pack, spatially resolve that battery pack and look at localized hotspots, we can then kind of zoom out and look at overall performance, including the thermal performance or the state of charge throughout a flight mission. Also look at thermal runaway. If one of the cells goes into a thermal runaway, how can we protect the rest of the pack from that cell propagating? What if scenarios? For example, what if we had water cooling or some type of liquid cooling as opposed to just air cooling? And you can see some of the great results that came out of this study. So the top plot happens to show both test versus simulation results of the battery temperature over a given flight mission. And the bottom plot is showing a predefined kind of charge or discharge, I should say, then recharge the battery pack, and then a rest period that was predefined by the user and can be defined in any type of transient event within GT Suite. And so if we're able to set up a cycle like this and then run the battery over many repetitive cycles, we start seeing interesting trends such as what type of thermal management strategy might we need to use, or how does the battery age and how does the state of health of the battery degrade over time as we run this cycle over and over again, which is a big factor into making craft like this economically viable, is the life of the battery packs and how long we can remain in service with those. A really interesting study with a lot of good validation behind it. And just a couple more features before I turn it over to my colleague for a live demonstration. Within GT Suite, there's a lot of what we call productivity enhancement tools. One of those that'll probably be demonstrated next includes this conversion of coming from a 3D CAD model directly into a 1D or 3D kind of fluid network or thermal network, and the ease of use that that brings, in addition to kind of sketching up something as an initial design. Also, when we build up models like this, especially at the system level, we like to parameterize inputs and look at effects or sensitivities or different heat exchanger sizing and how they might impact overall performance. And GT Suite has a built-in genetic algorithm for optimization, as well as design of experiments that allow us to explore the design space and truly define what our optimal layout, topology, or control strategy might be. And to tap into the power of running all of these different designs, GT Suite has distributed processing to take multiple different iterations of that model and run them on different CPU cores or even in a high-performance computing laboratory. And we're certainly proud of our high-quality technical support, engineering support that we've staffed up to support GT Suite throughout the world. And if you are interested in taking us up on a free trial, we'd love to show you some of that support and how we can help get you started. And lastly, there is a built-in 3D CFD tool that comes along with each GT license from Convergent Science, a third-party tool, to look into some problems that are purely 3D in nature. Lastly, since GT Suite may not be the only software that's being used in a given organization, it has to communicate with other tools that may be doing best-in-class type of analysis, and connecting with GT Suite is important. So GT Suite over the years has built direct coupling links with a lot of commercial software codes, as you're seeing on the upper left-hand side. If you're currently using ANSYS for a 3D finite element analysis, that certainly can be integrated within a GT Suite system model. Also, you have the ability to write your own user code and implement that in the model using Python, C, MATLAB, Fortran, or other languages. GT Suite also has an open API that can link to not only the above softwares, which we have direct links for, but perhaps any other software, perhaps an in-house software or your own software code if you'd like to. And we understand there's a lot of MATLAB Simulink runs out there, and GT Suite has a well-validated co-simulation with MATLAB Simulink using a GT Suite S function, or many different ways to cleanly co-simulate different runs, perhaps controls logic built in Simulink, commanding a system model within GT Suite. So without further ado, I think I'd like to pause there and transition to my colleague John Harrison for the live demonstration of the software here right now. So I'm going to stop sharing my screen right now, and I'll introduce here John Harrison as the next presenter. And as John is getting set up here, I certainly welcome you to type in any questions in the chat box. We're trying to reserve some time and expect to have good time to answer questions here towards the end of the presentation. Excellent. I see the questions coming in. I appreciate the good questions. All right.
Excellent, John. Well, thank you very much for discussion there, and going to continue on now with the live demonstration and share our screen here. Okay, so I hope everybody can see the screen now, where what we're looking at here is the primary model building interface of GT Suite. And this is where you go in and create models from scratch, or utilizing our 3D preprocessor to create models for you. And so in this particular example, you're looking at a basic orbital refueling type scenario where you can imagine there is a large supply tank that might be refueling a smaller satellite tank that might be depleted of fuel. And for the fluid problem, you want to be able to transfer the fluid from one tank to another. And that's what this scenario here is setting up. So you can see there's basic components that represent this physical system, starting from the left on the supply tank and then flowing through the lines to the satellite tank. Now, this particular system, or any physical system, is built from components in our template library. And you can see the template library option here. If you just click on that in the toolbar, that gives you access to all the different physical components in the GT Suite library. And so it's divided by physical domain. So GT Suite is a multi-physics simulation software package that John has nicely discussed a few minutes ago. And you can see the different physical domains we've got divided here, including the physics of fluid flow, primarily in 1D, solving 1D Navier-Stokes equations. That allows you to model any arbitrary gas, liquid, or two-phase refrigerant, and so on, using things like pipes and valves and heat exchangers and so on. We also are able to solve the physics of multi-body dynamics and structures with flexible bodies. Also incorporating the conjugate heat transfer from the fluid regime to the thermal regime with either lump parameter thermal modeling or finite element thermal modeling. And that includes all three modes of heat transfer as well. And then we also, just to round it out, have an electromagnetic library that allows users to study in detail things like batteries and even electrochemistry of batteries, to electric motors and even co-simulating with really detailed electric machines. And then users can also utilize either our native controls library that allows you to manipulate the model for using things like PID controllers, logic operators, lookup tables, all that good stuff, or even custom user programming can be done with our controls library. And then also we have very nice links, as John mentioned, to third-party tools to allow you to easily co-simulate. So the idea behind this is you take a component from the library. Let's say you want to model, flow in a pipe. You go in here and you type in pipe, and then you grab the component that you're looking for and just drag it right onto the map. And then once you do that, then it brings open a dialog that now requires some physical dimensions. In this case, a pipe's physical dimensions are a diameter and a length and surface roughness and all that type of stuff you would define here. So, once you got the inputs to that guy, then you come in, you might say, oh, I want to model a valve. You come in here, you type in valve, and we got, a gajillion different valves that you could choose from. Let's say I want to model a check valve. Come in here, define the inputs, and then you start connecting things up together, just linking them like so. And then you just go through one by one, component by component, build up your model. And a lot of these inputs are what we call parametric. So for example, in that pipe we just made, we could create a parameter for the diameter. So we come in here and we say something like dia, and that gets promoted to what we call our case setup. And inside case setup, this allows you to sweep and change iteration to iteration different values. So you might say, okay, well, what happens if my diameter is 30? Or what happens if I, double the diameter, fourfold the area here in that situation? How does that change the results? You can easily run a couple cases, or you could run a couple 100,000 cases if you wanted to, depending on how you want to set it up. We also have this very nice design of experiments built right into this guy. So we've seen many users go to over 10,000 cases, no problem. So it's very powerful in that sense. Now I'm just going to go ahead and get out of this guy. So this model is already kind of set up and ready to run. It's actually, one of our standard installation examples. If we go into the File menu, Examples, and then you can see, depending on the application you're interested in looking at, we've got a variety of different examples to get you started. So, for example, if I wanted to go in and look at, an aircraft ECS ducting example, just go in here and click on that example, and then the example pops up. And all of the examples are ready to run. And in fact, the results are already created. But if you wanted to run a model for the first time, you would hit this run button to launch the solver. Now, once a model is finished running, then you can view the results. And actually, I'll just open up just a standard example results file here. And when you do that, then you know, it's very simple to analyze different components of the system just by clicking on a component on the map. So, for example, if I want to look at, in this case, how much fluid flow went into this ducting example, you could easily just click on a part, and it'll give you access to basic information like, okay, how much mass flow rates are you supplying into the system? What kind of pressure drops are you seeing in the system with this RLT contour map? You can vary different quantities. That's looking at pressure. That's not terribly interesting. We go to something a little more interesting, maybe like velocities, show different color contours, and so on. So the post-processor is quite powerful, allows you to really do some advanced post-processing capabilities right native into GT. Now, there are other interfaces here to consider as well. So I've mentioned the ability to build a model from scratch using the template library, but an alternative method, and equally as powerful, sometimes even more powerful, is the ability to start from a raw CAD model, and it can be in native format or space claim format or what have you, and you can import that right into this 3D preprocessor, and then it allows you to discretize into either a flow system, a mechanical system, or a thermal system. So I'll show you the process. This is that same orbital refueling example we showed a minute ago. You can see it's already been sort of discretized into various flow components, including a pipe, a little miter bend, and a couple tanks, and so on. This is a pretty straightforward system. But just to give you an idea of the process and how it works, maybe if I start from a space claim model here, which comes for free with every license of GT, comes a license of a space claim, which is made by a company called ANSYS. But imagine you've got a straight pipe here, and now you want to convert this to look at a conjugate heat transfer problem of flow in a pipe. So the first thing I'm going to do is extract the fluid core of this 3D shape using this volume extraction here. And I'm going to go through, and now that I've got both a structure piece of the wall and the fluid flowing through the pipe, I'll go ahead and just save this as a new name. I'll call this demo. And then now what you can do is you could take this CAD model and import that into the 3D preprocessor of GT Suite. So starting from scratch, I'm going to import a 3D model. And I'm going to go to that example we just created here. Give me a second to browse to that file. Finish that. So here you can see that same pipe with the flow volume and a thermal structure here. So the first thing I'm going to do is convert the internal volume here into a pipe. I'm going to right-click on this and go Convert Shape to Component. And you can see it already detected the inlet and the outlet of the pipe automatically. It detected the diameters, detects the length. If there's bends and things like that, it'll detect all that for us. Makes bend loss calculations very easy and streamlined. I'll go ahead and hit Finish here. And then for the thermal structure here, I'm going to convert this to Convert Shape to Component. And instead of converting to a flow volume, this time I'm going to convert to a thermal component. Now I could either do a simple lumped parameter approach or do a general finite element. In this case, I'll do an FE, and you have control over how the mesh is created here. I'm just going to go ahead and rely on the whatever the defaults are. And here you can see the mesh that gets created. And then if we hit Finish, and then the final step is really to do the conjugate heat transfer between the structure and the fluid. And I can do that very easily by creating a convection connection between the two. And it actually detects the surface area for us automatically between the two components. It detected the surface area and the parts that were already created. If I hit OK, finish. And then now I'm just going to save this as a new model. Call this demo 2. And I want to also be able to do an ambient boundary condition on this guy here too. So I'm going to paint a new thermal port on the outside, and I'll call this outer. And that becomes our new thermal port. And I hit OK. And then now we're ready to export this model. Hit export. And you can see that the model gets created automatically, and the link between the thermal structure and the flow through the pipe is automatically created for us. And so now it's just up to us to supply the boundary conditions for the thermal structure and the boundary conditions of flow through the pipe. Now this was a very simple pipe problem, but you can imagine this can be easily extended to look at very complex phenomenon and problems inside the software. So I hope this is an easy illustration of how simple and easy the tool can be to use. We also have many written tutorials to get users started. We have many video tutorials that are available to users now as well. And of course, our technical support comes free with the software and even with free trials as well. So keep that option open as well. And so yeah, with that, this concludes the simple demonstration. And I think at this point, I'd like to hand it back over to my colleague, John, to round us out here.
Thank you very much, John. I think that was a great demo, and I hope that served as a good example for hands-on and what GT Suite might be all about. At this time, I'm going to share a last couple of slides before we get into the Q&A section. I see a couple of good questions that have already rolled in, and certainly appreciate more of those. One thing is to mention that if you are interested in GT Suite, to know that the engineering support is included with all of our licenses, not just during a free trial, but throughout the duration of your usage of GT. And that's something that we're really proud of, because a lot of these problems are not the easiest challenges that we're solving in simulation, and through great support, we can come up with great solutions. We also have a lot of different training available, both online and when COVID passes in person. Many of those are free. We also have many examples, as John had highlighted, tutorials that are built into GT that we didn't quite get to. Webinars we host all the time and are free and available for you to join. And just to know that you're not starting from scratch. If you are interested in starting with GT, we're happy to build a baseline model with you to validate that GT can model what you'd like to model with a simulation tool. And so lastly, our last slide here today is the offering we have for anyone attending today is a free software trial, including our engineering support. So no strings attached, just try the software, and we're happy to help get you started with it. We're happy to share a free intro training to get you up to speed. Those are online training courses. And we're also happy to offer a free pilot project. So that might be, I've got a interesting water surge problem, or I'm sorry, a propellant surge problem. I'd like to see if GT Suite can do it. Go ahead and challenge us with a problem like that, and we're happy to work with you with your data and get you results that can be validated. Also, before we enter the Q&A here, to remind you of some resources available on our website at www.gtisoft.com. We have the free webinars I had mentioned, the free online training, as well as a library of validations and case studies we call publications from our website to share some of those journal papers I had mentioned before in the case studies, or practical case studies that have been presented by those using GT Suite. So again, if you are interested in a free trial, I certainly welcome you to share your contact info in the chat box, as I see a couple of you have already done. Thank you. And any questions, or if you'd like to request a free trial via email, I'd be happy to field your request at j.zenker@gtisoft.com at my email address, and help get you started, or even just answer a question that you may have from this presentation or about simulation in general. More than happy to help. Okay, without further ado, I will get into the Q&A, and I do see a question coming up, and both John Harrison and I will field these guys. But it might make sense to open up the software at some point too, John, to share with people. So I see one question is, can we include chemical reaction kinetics? I assume those can be anything, right? I think we talked about a couple examples of those. One of them being combustion, another one being electrochemistry within a lithium-ion battery cell. John, I welcome your input on modeling those. It's certainly a capability that exists in GT, and we can even pop open the software if you'd like to share that with you. All of those are capable, and there is a chemical reaction kinetic solver built into GT.
Right, yeah, that's correct, John. And the chemical reactions, we basically go in and define the different reactions for the mechanism, and that can be on the order of a few reactions or a few hundred reactions. It's really kind of up to you, and that could be modeling, as John said, combustion, or another one we see, flow through a cat bed. For example, looking at hydrogen peroxide decomposition that can be thrown into a burner for thrust calculations and so on, and line sizing and all that. So the short answer to that is certainly yes, and we also do have an equilibrium combustion model that's included as well.
You got it. Another common question we get is comments on the runtime for a lot of these models. Some of you may be familiar with various different simulation tools. And John, can you comment on how long a model like this might take to run?
Yeah, many of the models run faster than real time. Sometimes tens to hundreds to thousands times faster. It's really up to the size of the problem, but certainly we expect runs to typically take on the order of seconds to minutes, unless you're doing really long simulating months in space type of thing. Those can take sometimes hours to run. Depends on the problem, but certainly much faster than you would probably see in full 3D type CFD, FE, and so on. And John, another question too that we typically see is, I know we got asked that this morning, was, how does the package work? Do we have to buy separate tools, a CAD tool and a 3D tool, or how does that work, John?
Yeah, another good question. So GT Suite is just one license, right? So one license includes all of the functionality and features that were shared in this presentation today, from the tool side, the tool that can convert 3D CAD models into more of a 1D model or a collection of components that represent a 3D geometry. Includes a post-processing tool, includes some of the third-party tools that we mentioned today, and it's all one license. The approach that GT Suite takes that might be different from other tools too is all the physics-based libraries are included with all licenses. So you have access to, if you're facing a problem that's maybe in the thermal fluids domain and something pops up that's chemical kinetics within that system, that library is included in the license. Or you have a battery problem or some other type of problems, generally all those libraries are included within that one license type. And another common question too, John, is how do these licenses work? What if I'm one of 50 people within a center at NASA? Can I share a license, or how does that work?
Yeah, that's a great question. So, I mean, at a given location, we have flexible licensing so that, it could be fully floating. So it's not tied to a user's computer. Anybody at a given location, or oftentimes the licenses are shared across, either the United States or even sometimes globally. So the users really do have flexibility in terms of how they access the licenses. Great question.
Yeah, that's great. Another common question we get is, you showed a lot of kind of space applications, but what does GT offer on the aircraft side? for example, commercial jets or even military jet applications.
Well, there's a lot of subsystems on those craft too, John, that's for sure. Not only the propulsion system, but you've got the environmental control system and the fuel system and the landing gears and any type of electrical systems and so on. So there's many subsystems of not only spacecraft, but aircraft that can be studied inside the tool.
That's excellent. That's excellent. Well, thanks. I think we answered a majority of the questions. Apologies if we did not get to those. I just entered my email address into the chat box, j.zanker@gtisoft.com, and encourage you to reach out with any questions or anything you might have from the presentation, or perhaps for a copy of the presentation. We're more than happy to share what we have. And to be courteous to our next presenter coming up, I think I will wrap and maybe turn it back to the NASA staff or Parker for any last-minute logistics kind of things. But really appreciate your time and attention today. I hope you learned something today, and I hope we get the chance to work together more in the future. All the best. Thank you.
Thank you.